Stand anywhere on the open prairie of Kansas or Nebraska in 1880, and two things dominate the horizon: grass and sky. But look more carefully, and a third shape appears, a thin vertical line, topped with a slowly turning wheel. That windmill is not decoration, it is infrastructure. Without it, the farm below it cannot exist, because without it, there is no water. The Great Plains of North America contain some of the most fertile agricultural land on Earth. They also have one fundamental problem that no amount of good soil or reliable wind can by itself solve. The surface is dry. Rainfall across the central and western Great Plains averages between 10 and 20 inches per year, insufficient for most non-drought-tolerant crops without supplemental water. Streams and rivers cross the plains, but they are widely spaced. Between them, across hundreds of miles of grassland, the water is underground. Beneath much of the Great Plains lies the Ogallala Aquifer, one of the largest underground freshwater reservoirs on Earth, covering approximately 174 Vodgitsa in South Dakota to Texas. The water is there. The problem for most of the 19th century was getting it to the surface. Hand pumps worked at shallow depths. But across much of the plains, the water table sat 50 to 200 feet below ground, far beyond the practical range of manual pumping for the volumes that livestock and farming required. A cow requires 30 to 50 gallons of water per day. A small cattle operation of 50 head requires 1,500 to 2,500 gallons daily, every day regardless of weather. Hauling that volume from a distant stream by hand or by barrel wagon was not economically viable at any scale that made plains ranching sustainable. What the Great Plains needed was a machine that could lift water from depth continuously, run without a human operator, function in variable winds, and survive years of exposure on the open plains without constant maintenance. That machine did not exist in 1850. In 1854, a machinist and inventor named Daniel Halladay, working in Ellington, Connecticut, received U.S. patent number 11,629 for a self-governing windmill. It was the machine that the Great Plains required, though the Great Plains had not yet been settled and the full scale of the need was not yet apparent. The term self-governing is the key to understanding what Halladay built. Earlier windmills, European post mills and smock mills, and the American adaptations that followed, required a human operator to adjust the blade angle or the tail vane when wind speeds changed. In steady, moderate winds, earlier designs worked adequately. But plains winds are not steady or moderate. Gusts across the Central Plains can accelerate from 15 miles per hour to 60 miles per hour within minutes, a change that, on a fixed-blade windmill, transfers enormous and potentially destructive force to the mechanism. A windmill that required a human operator to reduce sail area before a wind gust destroyed the mechanism was a windmill that could only operate safely when someone was watching it. On the open range, with farms and ranches miles apart, that requirement made the technology practically useless. Halladay's solution addressed this directly. His design incorporated a mechanism that automatically adjusted the blade angle in response to wind speed, reducing the effective sail area in high winds without any human input. The Halladay design used a wheel made of multiple individual wooden blades arranged in sections. Each section was hinged, mounted on a pivot, so that it could rotate to change its angle relative to the wind. In normal wind conditions, the blade sections were held at an angle that presented maximum area to the wind, capturing as much wind energy as possible to drive the pump below. As wind speed increased beyond the design threshold, centrifugal force, the outward force generated by the spinning wheel, caused the blade sections to rotate on their pivots, reducing their angle relative to the wind, and therefore reducing the force the wind could exert on them. This is the same principle used in a centrifugal governor, a device that uses the outward force of rotation to control the speed of a rotating system. Steam engine governors, which regulated engine speed automatically, used identical physics. Halladay applied that principle to wind power. As the blade sections feathered, rotating to reduce their angle of attack, the windmill slowed. The reduced speed produced less centrifugal force, which allowed the springs or weights in the mechanism to partially restore the blade angle. The system found an equilibrium speed automatically, regardless of wind velocity. The result was a windmill that could run through a plains thunderstorm gust at 60 miles per hour and emerge intact, while a conventional fixed-blade windmill would have torn apart under the same force. Halladay initially manufactured his windmill in Ellington, Connecticut, far from the Great Plains market he would eventually serve. In 1863, he moved production to Batavia, Illinois, closer to the agricultural markets of the Midwest. The company Halladay founded, the U.S. Wind Engine and Pump Company, became one of the dominant windmill manufacturers of the late 19th century. By the 1880s, more than 24 companies were manufacturing American-style windmills, each competing on efficiency, durability, and price. The most significant design evolution came in 1876, when Thomas O. Perry, working for the Air Motor Company of Chicago, developed a windmill using all-steel construction and curved steel blades rather than the traditional wooden sectional wheel. Perry conducted what T. Lindsay Baker's 1985 field guide describes as among the most rigorous engineering analyses applied to windmill design in the 19th century, testing blade curvatures, angles, and wheel geometries systematically to optimize energy capture from wind. The air motor's steel blades were curved, designed to follow the same aerodynamic principle that makes a boat sail more efficient than a flat board. A curved surface generates lift as well as drag, capturing more energy from the same wind than a flat blade. The air motor also used a side vane governor system rather than the sectional wheel approach, a tail vane offset from the wheel center line that caused the wheel to turn out of the wind in high wind conditions, reducing its effective area automatically. When wind speed exceeded safe operating limits, the offset tail vane caused the wheel to rotate sideways, presenting its edge to the wind rather than its face. In this position, the wheel captured almost no wind energy and essentially stopped. When the gust passed, the vane returned the wheel to face the wind and pumping resumed. The air motor's all-steel construction gave it a significant durability advantage over wooden designs in the plains environment. Wood swells, shrinks, warps, and rots in the cycles of plains weather, wet springs, dry summers, freezing winters. Steel, properly galvanized, resists corrosion and maintains dimensional stability through temperature and humidity cycles. A well-maintained air motor could operate for 20 to 30 years with periodic lubrication and occasional blade replacement, making it an economically sound long-term investment for a plains rancher. The pump mechanism below the windmill tower was equally important. A standard sucker rod pump, a reciprocating plunger pump, driven by the up and down motion of a rod connected to the windmill's crankshaft, could lift water from depths of 50 to 300 feet depending on the pump cylinder diameter and the windmill's power output. The crankshaft at the top of the windmill tower converted the rotary motion of the wheel into the up and down reciprocating motion the pump required. As the wheel turned, the crankshaft pushed the pump rod down and pulled it back up, each stroke lifting a slug of water from the aquifer below. A standard 8-foot diameter air motor in a 15-mile-per-hour wind could pump approximately 3 gallons per minute from a depth of 100 feet or roughly 180 gallons per hour. Over a 10-hour operating day, that machine could deliver 1,800 gallons to a surface tank. 1,800 gallons per day. Recall that 50 head of cattle require 1,500 to 2,500 gallons daily. A single 8-foot windmill could water a modest cattle operation. Larger 10 and 12-foot diameter machines could support significantly higher herd numbers from greater depths. The tower that held the windmill aloft was itself a significant engineering structure. Early towers were wooden, built from local timber in a four-legged lattice configuration. By the 1880s, steel angle iron towers had largely replaced wooden towers in the same way steel replaced wood in the windmill head. Standard tower heights ranged from 18 to 40 feet, depending on the required water depth, the wind exposure at the site, and the distance from obstructions, trees, buildings, or terrain features that could create turbulence and reduce effective wind speed at the wheel level. Walter Prescott Webb, in his 1931 foundational history, The Great Plains, argued that 3 technologies made permanent settlement of the semi-arid plains possible: barbed wire for fencing, the repeating rifle for security, and the windmill for water. Of those 3, the windmill was the only one that addressed the land's most fundamental constraint. The settlement of the Great Plains proceeded alongside the windmill industry in lockstep. The Homestead Act of 1862 opened the plains to settlement. The Transcontinental Railroad arrived in 1869. Barbed wire was commercially available from 1874. The windmill industry was already established and expanding. Nebraska State Historical Society records document that windmill installations in Nebraska alone numbered in the tens of thousands by 1890, with the density highest in the western counties where surface water was most scarce. By 1900, an estimated 6 million windmills were operating across the American West, a figure documented in USDA agricultural census records and corroborated by Lindsay Baker's 1985 survey of windmill manufacturers' production records. 6 million machines, each one drilling a connection between the surface and the aquifer below. Together, they transformed the semi-arid grassland of the central and western plains into one of the most productive agricultural regions on Earth. The railroad companies understood this. The major transcontinental railroads, the Union Pacific, the Santa Fe, the Northern Pacific, installed windmills along their tracks at regular intervals to supply water for steam locomotives, which consumed hundreds of gallons per operational hour. Along some stretches of the transcontinental routes, windmills appeared every 5 to 10 miles, providing the water infrastructure that made continuous train operation across the waterless plains physically possible. The windmill industry peaked in the late 1880s and early 1900s, both in manufacturing volume and in cultural prominence. In the small towns of the Central Plains, the water tower and the windmill were the tallest structures on the horizon, and the most important. The decline of the windmill as the primary water-lifting technology came with rural electrification, the same force that displaced the root cellar and transformed the American farmstead in the 1930s and 1940s. An electric submersible pump could lift more water per hour than any windmill at any time of day or night, regardless of wind conditions. Where electricity was available and affordable, it replaced wind-powered pumping quickly and almost completely. But electricity did not reach every corner of the Great Plains simultaneously, and in the most remote areas, it still has not reached in a form that makes electric pumping economical. The windmill did not disappear. It retreated to the places where it still made the most sense. Today, an estimated 150,000 to 200,000 windmills remain in operation across the American Great Plains, primarily on ranches and farms in the most remote sections of Texas, New Mexico, Wyoming, Montana, and the western Dakotas. The economics that keep them operating are the same economics that drove the original installation. In a location where drilling a well and running power lines costs more than installing and maintaining a windmill, the windmill remains the rational choice. The Air Motor Company, founded in Chicago in 1888, is still manufacturing windmills today in San Angelo, Texas. The basic design has been refined but not fundamentally changed. The side vane governor, the curved steel blades, the sucker rod pump connection, all present in the modern air motor. The Smithsonian Institution holds multiple examples of American windmill models in its National Museum of American History collection, including Halladay-era sectional wheel designs and early air motor steel models, preserving the engineering record of the machines that made plain settlement possible. Now, for anyone who has a windmill on their property or who is considering restoring or installing one, let's look at what the historical and contemporary record tells us about maintenance, restoration, and practical operation. The most common failure mode in a neglected windmill is lack of lubrication. The gearbox at the top of the tower, which converts the wheel's rotary motion to the up and down pump rod motion, operates under continuous load and requires regular oiling. Baker's 1985 field guide documents that most windmill failures on surviving machines trace to dried or contaminated gearbox oil. Most original air motor and Eclipse windmill gearboxes used a sealed oil reservoir, a design that required annual oil changes rather than continuous greasing. The recommended oil for most vintage gearboxes is a non-detergent motor oil, SAE 30 weight, which approximates the original oil specifications without the additives that modern detergent oils contain. The blades of a surviving steel windmill should be inspected for rust, bent sections, and loose bolts. Surface rust on galvanized steel blades is typically superficial and can be treated with wire brushing, followed by a rust-inhibiting primer and aluminum or zinc paint. Structural rust, pitting or perforations in the blade surface requires blade replacement. The tower itself should be inspected for loose or missing bolts, corrosion at ground level, where moisture contact is highest, and any visible bending or distortion of the leg members. Tower legs that show significant corrosion at the base may need section replacement before the windmill can be safely reoperated. The sucker rod and pump cylinder below ground are the most difficult components to inspect without pulling the rod, which requires either a windlass or a pipe puller and is a two-person job at minimum. Signs of pump failure include significantly reduced water output, air in the discharge flow, or unusual noise from below the casing. For anyone considering a new windmill installation on remote property, the practical case remains what it was in 1880. If the distance to power lines makes electric pumping expensive, and if the wind resource at the site averages 10 to 15 miles per hour or better, a windmill is a cost-effective maintenance minimal water system. T. Lindsay Baker's 1985 Field Guide, available through university libraries and online used book markets, remains the most comprehensive practical reference for identifying windmill models, sourcing replacement parts, and understanding the engineering of specific designs. It is the starting point for any serious windmill restoration. Parts availability for common American windmill models, particularly the air motor and the Eclipse, is generally good. Air motor parts are available new from the company itself, which still manufactures the machine. Eclipse and other vintage models are served by a network of specialist dealers, swap meets, and online parts suppliers. The windmill collector and restoration community in the United States is active and well documented. The American Wind Power Center in Lubbock, Texas, a museum dedicated specifically to the American windmill, holds over 200 restored examples representing virtually every significant manufacturer from the 1854 to 1940 era. That museum, and the restoration community around it, is the living continuation of a technology that once moved 6 million times the water that the Great Plains surface could provide. That is not a small thing. The first lesson the windmill's history teaches is about the relationship between enabling technology and geographic potential. The Great Plains had water, fertile soil, and wind. What it lacked before 1854 was a machine that could connect the wind to the water to the surface in a way that required no continuous human oversight. Halladay's self-governing mechanism was not a new source of energy. It was a new way of using a source of energy that had always been present. The wind had always blown across the Great Plains. The water had always been underground. The machine was what made the connection between the two automatic, reliable, and scalable. The second lesson is about durability as an engineering value. The air motor's 20 to 30-year service life was not incidental. It was a design requirement because a rancher installing a windmill on remote plains land needed a machine that would not require factory service for years at a time. The machines that lasted on the open plains were those designed around the reality of where they would operate, not around the convenience of their manufacturers. That is a design principle worth carrying forward into any equipment selection or fabrication decision. The third lesson is the simplest. The Great Plains without the windmill could not have supported permanent settlement at the scale and density that American history records. The windmill is not a footnote to that history. It is a load-bearing structural element of it. That's the real story of the American windmill, documented from Halladay's 1854 patent through the 6 million machines of 1900, and still visible today on the horizon of the most remote sections of the American plains. It is not a nostalgic machine. It is a machine that still works in the places where the conditions that called it into existence have not changed. If this kind of documented equipment history is what you come here for, subscribe to The Quiet Farmer. We're building a library of these stories, the machines, the engineering decisions, and the historical record behind them. In the comments, tell us, does your property still have a windmill working or not? If you've restored one, tell us which model and what condition it was in when you started. The people watching this are exactly the right people to ask. The lesson here isn't nostalgia. It's that some machines were built to solve a specific problem so well that the solution outlasted the era that created it. The windmill is one of those machines. We'll see you in the next one.